A curious mind awakens. Young Einstein's journey begins. Albert Einstein, a name synonymous with genius, was once a curious child mesmerized by a simple compass. This seemingly ordinary object held a profound mystery for young Albert. Born in Ulm, Germany, in 1879, young Albert possessed an insatiable thirst for knowledge and a deep fascination with the workings of the universe. His curiosity knew no bounds, and he often found himself lost in thought, pondering the mysteries of the cosmos. The compass, a gift from his father, sparked an early interest in the invisible forces that govern our world. It was more than just a toy. It was a gateway to understanding the unseen. This simple device, with its unwavering needle always pointing north, ignited a spark in young Einstein's mind. He was captivated by the idea that something invisible could exert such a powerful influence. Einstein's early education was marked by both brilliance and unconventionality. He was a prodigious student, often outpacing his peers in subjects like mathematics and physics. He excelled in mathematics and physics, but often clashed with the rigid teaching styles of the time. Traditional classrooms, with their strict adherence to rote learning, stifled his creative and inquisitive nature. His independent spirit and inquisitive nature led him to question established norms and seek deeper understanding beyond the confines of textbooks. He was not content with merely accepting what was taught. He wanted to understand the why behind it all. This drive to challenge conventional wisdom would later become a hallmark of his scientific career. He was always looking for new ways to understand the world around him, never satisfied with easy answers. As Einstein matured, his curiosity led him to ponder the nature of light and motion. He spent countless hours contemplating these fundamental aspects of reality, driven by a desire to uncover the truth. The prevailing scientific view at the time was that light traveled through a medium called the luminiferous ether. This concept was widely accepted, yet it left many questions unanswered. However, experiments designed to detect this ether consistently failed to find any evidence for its existence. These failed experiments puzzled many scientists and hinted at deeper mysteries. This discrepancy intrigued Einstein and sowed the seeds of doubt about the completeness of classical physics. He began to suspect that there was something fundamentally wrong with the existing theories. Fueled by a relentless desire to reconcile these inconsistencies, Einstein embarked on a journey that would revolutionize our understanding of the cosmos. His determination and innovative thinking set him apart from his contemporaries. His relentless pursuit of truth and his unwavering belief in the power of human reason would ultimately lead him to develop the groundbreaking theories of relativity, forever changing our perception of space, time, and gravity. Einstein's journey from a curious child to a revolutionary scientist is a testament to the power of curiosity and the human spirit. The Miracle Year, unveiling the special theory of relativity. The year 1905 marked a turning point in Einstein's life and in the history of science. During this miracle year, as it came to be known, the 26-year-old Einstein published 4 groundbreaking papers that would reshape the landscape of modern physics. These papers, each revolutionary in its own right, laid the foundation for Einstein's theory of special relativity, a profound reimagining of the very fabric of our universe. At the heart of special relativity lies a simple yet profound idea. The laws of physics are the same for all observers in uniform motion. This means that no matter how fast you are moving, as long as your speed is constant, the laws of physics will appear the same to you as they do to someone standing still. This seemingly straightforward concept has far-reaching implications for our understanding of space and time. One of the most startling consequences of special relativity is the phenomenon of time dilation. Einstein realized that time, rather than being an absolute and unchanging entity, is relative to the observer's motion. As an object approaches the speed of light, time itself slows down for that object relative to a stationary observer. This mind-bending concept, while counterintuitive to our everyday experience, has been experimentally verified countless times. Energy and mass, unlocking the secrets of mc². This equation, simple yet profound, holds the key to understanding the universe at its most fundamental level. Perhaps the most famous equation in all of science, mc², emerged from Einstein's groundbreaking work on special relativity. This theory, published in 1905, fundamentally changed the way we perceive space, time, and energy. This elegant formula, deceptively simple in its appearance, encapsulates a profound truth about the nature of energy and mass. It is a cornerstone of modern physics, bridging the gap between the macroscopic and microscopic worlds. It reveals that these two fundamental quantities, once thought to be distinct and separate, are in fact intimately intertwined. This interconnection means that mass can be seen as a concentrated form of energy. The equation states that energy, E, is equal to mass, m, multiplied by the speed of light, c, squared. This relationship shows that even a small amount of mass can be converted into a vast amount of energy. The speed of light, an enormous number, is squared in this equation, highlighting the immense amount of energy contained within even small amounts of matter. This underscores the potential power locked within the atomic nucleus. This realization revolutionized our understanding of the universe and paved the way for the development of nuclear power. It also opened up new avenues in theoretical physics, leading to further discoveries about the fabric of reality. mc², implies that mass can be converted into energy and vice versa. This principle is not just theoretical. It has practical applications in various fields, from medical imaging to energy production. This principle is at the heart of nuclear reactions, where tiny amounts of mass are transformed into staggering amounts of energy. This is the process that powers both nuclear reactors and atomic bombs. The sun, for example, derives its energy from nuclear fusion reactions in its core, where hydrogen atoms fuse to form helium, releasing tremendous energy in the process. This fusion process is a direct application of mc². This equation also has profound implications for our understanding of the early universe. It helps explain how the universe evolved from a hot, dense state to the vast, complex cosmos we observe today. According to the Big Bang theory, the universe began as an incredibly hot and dense state. In this primordial soup, energy and mass were interchangeable, driving the rapid expansion and cooling of the universe. In this early universe, energy and mass were constantly interconverting, driving the expansion and evolution of the cosmos. This dynamic interplay set the stage for the formation of galaxies, stars, and ultimately, life itself. Beyond special relativity, the quest for a grander theory. While Einstein's special theory of relativity was a monumental achievement, he realized that it was incomplete. It was a groundbreaking step forward, but it left many questions unanswered. The theory only applied to objects moving at constant velocities in a straight line, which is a very specific and limited scenario in the vast and dynamic universe. It didn't account for acceleration, which is a change in velocity. This omission meant that the theory couldn't fully describe the behavior of objects in more complex, real-world situations. It also didn't incorporate gravity, a fundamental force in the universe that governs the motion of planets, stars, and galaxies. Einstein understood that a more comprehensive theory was needed, one that could encompass both special relativity and gravity, providing a unified description of the physical world. He embarked on a decade-long intellectual journey, grappling with complex mathematical concepts and challenging the very foundations of physics. This journey was filled with moments of doubt and frustration, but also with profound insights and breakthroughs. This quest would lead him to his crowning achievement, the general theory of relativity, a theory that would revolutionize our understanding of the universe. Einstein's key insight was that gravity is not a force acting at a distance. as Newton had proposed, but rather a manifestation of the curvature of space-time itself. This was a radical departure from the classical view of gravity. He envisioned space-time as a four-dimensional fabric, with three spatial dimensions and one dimension of time. This fabric could be warped and curved by the presence of mass and energy. Massive objects, he realized, warp this fabric, creating what we perceive as gravity. The more massive the object, the greater the curvature it creates in space-time. To visualize this concept, imagine a bowling ball placed on a stretched rubber sheet. The weight of the ball creates a depression in the sheet. The bowling ball creates a depression in the sheet, causing nearby objects to roll towards it. This is a simple analogy to help us understand the complex nature of space-time curvature. Similarly, massive objects in the universe create depressions in space-time, causing other objects to be drawn towards them. This warping of space-time is what we experience as gravity. This is what we experience as gravity. It's not a force pulling objects together, but rather the result of objects following the curved paths in the warped space-time. The development of general relativity was a testament to Einstein's genius and his unwavering pursuit of a deeper understanding of the cosmos. His work opened up new realms of scientific inquiry and inspired generations of physicists. This revolutionary theory provided a new framework for comprehending the universe on the grandest of scales, from the motion of planets to the evolution of galaxies. It has become a cornerstone of modern physics, shaping our understanding of the cosmos and our place within it.